the recording.
Okay. Starting the recording. Okay, so you haven't been recording all of this before this, which is all this important material that we, all these dialogues and exchanges. So I see that this room is filled with many scholars, many with advanced degrees, and you're not your grandmother who is studying for her own advanced degree, but she's here in spirit and she's going to watch the video. I want to say I welcome your family here. It's a real pleasure, and your friends from high school, even if they went to MIT, and Andre, even if he's coming from Stanford. We're very proud to have you all here today, and especially for Mike's big day. And I want to just say at the outset that he's been a super pleasure to have in the lab since he joined us from Princeton. And he has been a central member of the lab. He has worked on our robot manipulation projects, every aspect of them, and at all levels of detail, as you're about to hear, and has really been a core and trusted member of the lab. And he's always got a great attitude, can do, gets everything done, and has lots of ideas, writes papers, stays up late at night. And on top of all this, he is his amazing self-discipline has resulted in him being a champion level runner and long distance athlete and marathoner at levels that are astounding when we hear the numbers that he's running. So I don't know how you fit all this in, Mike, with also doing an amazing PhD, but you did it. And now, well, I should say you're about to do it. We'll have to see. All right, so with that, I'll turn it over to you, Mike.
All right, awesome. Yeah, thanks for the intro. So today I'm going to be talking about manipulation and perception policies for robot mechanical search. This is something that I think has been a project that's kind of weaved through my entire PhD. So hopefully you get a flavor of kind of all the different types of projects that I've been working on. So let's start it off. So I think a big motivation for my PhD in general has been dealing with these kind of cluttered bins or shelves. Maybe they're in houses like this, fridges that look like that, warehouses. We have like all these boxes full of packages, shelves full of packages. And in particular, I've been focused on mechanical search, which is this problem where we want to extract some known target object that we're looking for from one of these types of environments. So, the thing we might be looking for could be hidden behind other objects. We might have to move stuff out of the way. And a big key part of this is that we're actually going to have to interact with the environment that we're searching through. So not only do we have to kind of be able to locate what we're looking for, but we also have to think critically about where it might be hiding in the scene. And so we've looked at a couple different types of this problem. So we label these as overhead access, these bin type environments where we have a bunch of objects heaped on top of each other. We have lateral access shelf type environments, so shelves, cabinets, refrigerators, stuff like that. And then we can even consider this problem to be over entire homes or commercial spaces where we might have to move between different rooms first to even think about which room our object might be in, and then kind of go from there and do a lower level mechanical search problem inside of that. Yeah, so just to think about what that might actually look like, if we end up at one of these bins and we're looking for some target like this mustard here, we can see that it might be hidden underneath some other objects. And so we might have to take some grasping actions or some pushing actions to try and move objects out of the way and uncover whatever it is that we're looking for so we can get it out of there. And so I think this boils down in my PhD to two really key questions, which is what area or object should the robot look under or look around or behind first at each time step in this search process. And then once we kind of figure that out, what action should we actually take to make progress on our search? So yeah, this is a roadmap of what the talk's going to look like. But basically, we're going to try and break down this problem as a partially observed Markov decision process, talk about some of the challenges that this formulation presents. Then I'll talk a little bit about my research and how I've attacked the perception side of this, and then also the kind of high-level policy side of that. Yeah, so we don't have to go through all of the math here, but the basic idea is that this can be broken down into a POM DP, which consists of states, observations, actions, transitions, rewards, and maybe some discount factor. And here, the key thing is that our reward is actually just this sparse reward 0 to 1, which means that when we extract the object that we're looking for, we're going to get some reward of 1, but until that point, we don't get any reward. So we just kind of keep searching and keep searching until we find whatever it is we're looking for, and then we can get a signal that we've actually found the right thing. And our actions here, like I said before, these could be like pushing actions, they could be suction actions, they could be grasping actions, or in these kind of larger spaces, it could be moving around between different rooms or moving between different cabinets or shelves, something like that. Yeah, and the goal here is to try and find some policy where here I'm parameterizing by theta. And so we're going to try and maximize this, this objective here, which is essentially some expectation over trajectories that are induced by whatever policy we're currently trying out. And so you can see essentially what this objective is saying is that we're going to try and find the object as quickly as possible. So if this gamma is less than 1, then basically this is telling us that like we're going to get the maximal reward if we find this object as quickly as possible. Yeah, so what kind of challenges does this present? So this problem I think is really easy for people, but I think for robots, as we start thinking about the problem, it becomes really hard really quickly. And so one issue is that we have this continuous action space. So we could actually, even though I've kind of broken it down into a certain set of actions initially, there's a whole bunch of different actions that you could actually try. So humans, you know, when you're rummaging through something, you just kind of move everything out of the way. It's very continuous. You kind of just feel different objects and like decide that maybe that's something that I want to move, or maybe I want to leave this thing here, or you pick something up and move it, you know, kind of toss it into another area. So there's all sorts of different actions we could consider with the robot. Like I said before, there's this sparse reward problem. So we only get a reward at the end when we succeed. So this could be tough if there's actually like a lot of steps we have to take in order to find the object that we're looking for. There's all sorts of contact dynamics between objects. So especially in these cases where we have heaps of objects that are all on top of each other, we have to somehow reason about how taking an action on one of these objects is going to affect all the other objects. And that's pretty hard to do, especially if we don't know what the objects look like ahead of time. There's all sorts of object occlusions. So when we take images from the perspective of our robot, we might not be able to see everything in the scene. There's all sorts of stuff that's hidden behind other objects, all that kind of good stuff. And then finally, I think these last two are also really important. So doing rollouts of these types of policies for this type of problem is really expensive on real robots. And it's almost impossible to reset the environment to be exactly the same time after time, right? So I can solve maybe one of these scenarios with some policy, and then if I give you a new one, it's hard to generalize across that. That's the second part of this as well. But we also may not even be able to solve the same problem twice. So we have to think about how can we have policies that can deal with something like that. And so overall, I would argue that this makes end-to-end learning of this policy really difficult in this setting. And so I'll talk about how we actually try to decompose our policy to get away from something that just looks like this. So this is one attempt you might have at this problem, and we have tried this also, where you just take some observation at each time step, you feed that into some policy and try and have it generate an action. But it turns out this doesn't work very well. So what I've tried to do over my PhD is instead focus on something that looks a little bit more like this, where we have some perception pipeline that's going to output some intermediate representation, and then our policy can act on that instead. So we're not going to use the observation directly. We're going to try and come up with some other representation that's more helpful for the policy. And in addition, we're going to break down the policy into these two different stages. So instead of just having some policy that takes in this intermediate representation and immediately produces an action, we're going to leverage the fact that there's a lot of people who have also worked on policies for grasping or policies for pushing and use those as action primitives, and then just select those with some high level policy up here, which I'm going to call an action selector. Yeah, and so hopefully you can kind of see the two questions that I was talking about before are going to really map to these two things here. So perception is really going to focus on, what object should we look at? And then the action selector is really going to focus on which actions we should take given some, set of actions that we can come up with. I'm not going to really talk about this action primitives thing very much in this talk. This is also something I've worked a lot on throughout my PhD, but I think there's not enough time, and it's also kind of dives away into a whole bunch of other things that can go on. So yeah, let's start with the perception side of things. So going back to 2018, which is when I was still pretty new in my PhD and thinking about some of these problems, this was kind of the state of the art for segmentation, which is a really common problem in computer vision, where we want to essentially map all of the different pixels in an image to some object, right? So you can see here, this is a bunch of cars and people on the street. And what we're trying to do is just basically map all of these pixels to either a person or a car or like a plant or something like that, so that we know which things in the scene are objects and maybe what class that they're belonging to. And I think these were really cool at the time. I think they're still really cool. I'm really impressed by a lot of this work. But I think the main downsides for it was that it required these really massive hand labeled data sets for training. So a lot of times there was people going in and actually like highlighting where all of the things in the image are, and that's really time consuming. And it also didn't do very well generalizing to classes that it hadn't seen before. So if you train this thing on images that look like this, it would probably do really poorly on the bin images that I was showing before, because it hasn't seen those types of objects before. So it doesn't really know what shapes are common in that sort of environment. Yeah, so this was one of my first projects that I worked on, and it really shaped, I think, a lot of how I started thinking about research and also how to solve some of these types of problems, or maybe not solve, but at least come up with some sort of approach to some of these. So what we wanted to do was extend some of these segmentation networks to images that we were seeing for mechanical search, like the ones you see here. These heaps of objects, they might be a bunch of toys or a bunch of like mechanical parts or something like that. And so we want to be able to take the benefits of mask CNN or those types of networks and extend it to this. And what we found was that we could use depth images for generalization. So that's one key idea here. We didn't have to necessarily rely on texture of everything, like was typically done at the time. And then I think the second part is probably even more important, using simulation for scaling label collection. And so this followed from a lot of work. I think that, Jeff is on the call and he was doing this for NextNet already at the time. And so I think that was really key, as well as thinking about like, okay, we have ground truth labels in simulation. Can we use those to train one of these networks? And then, using depth images, generalize that to real world. And in addition to just real world, we also were kind of showing that if you use depth images and you're not as worried about texture, maybe that also helps you generalize better different types of objects as well. So you can see how this went in terms of automated data set generation. We're able to generate a ton of these object labels, so like 300,000 plus in about 3 hours. If people were doing this, just like for context, I think some of the data sets at the time were somewhere on the order of hundreds of days typically for people to label like this amount of images. And so, yeah, that's essentially how it went down. Take a bunch of object models like this, throw them in a heap, render an image, get your labels for more or less free, and then train your network that way. Yeah, so just to kind of recap what that ended up looking like, you can see an example here where we've kind of made the depth image a lot more contrasted, so you can actually see what it looks like. But you can see it works pretty well, even for these scenes where there's kind of a lot of objects that are overlapping, and you can actually understand which object is which. Now, why is this important for mechanical search? Well, I think this is the precursor problem for mechanical search in a lot of ways. If you can identify which objects are in the scene, then it's pretty easy at that point to map like one specific object you're looking for to an action set like grasps. So that's what we showed actually in this paper as well, was that if we can get really accurate segmentation like this, then we can basically just ask for each mask that we're getting or each object in the scene, is this the object we're looking for? And if it is, then we just plant a grasp on that and we grasp it. So this is great if the object's already visible, right? But as I already told you for mechanical search, like the whole point is that the object is not visible most of the time. So most of the time, and this image is kind of blurry, but this is actually one of the robot images we took, so that's why it's not super high res. But say we're looking for this object, we obviously can't see it here. So the segmentation thing that we've just done, not super helpful quite yet, because we have to be able to actually uncover the object first. So that brings us to the next part of what I'm going to talk about on the perception side of things, which is this idea of occupancy distribution. So I'll explain what that actually is. But the basic idea we're asking here is, where do we want to look in this image to find what we're looking for? And I think as humans, you have like really good intuition about this. Like this object, probably not a good idea, right? This is like nothing underneath it, this Yoda thing. And you know that how? Well, you have like some idea of what this object looks like what its dimensions are, and you don't really think it's like lying on something. And similarly for this pen right over here, the Sharpie, it's just like not big enough to include that thing, right? But how do we, maybe this is maybe a good choice actually, because it looks like it's maybe on top of something else, might be hiding something, it's kind of big. And similarly, this thing is lying on top of something else, so maybe there's something hiding underneath it. So I think like when you're looking at this image, you actually can probably narrow it down really quickly. Like there's only a couple places that you would actually look. So how do we encode this for robots? And in addition, if we had just like almost the same exact scene, but now we see part of the object, we know exactly which object to pick up. So like in this past one, you might have picked up this mustard bottle first because it's bigger and maybe there's like more of a chance that it's underneath there. But as soon as you see this other image, which is almost exactly the same, except you can see a little bit of the object you're looking for, then you like know exactly what you want to pick up and it's going to be there for sure. So yeah, this project was really about trying to encode this idea into something that the robot could actually operate on. And so we took a lot of inspiration from some recent work in computer vision, especially, which was starting to predict these distributions over likely poses of objects or likely gaze directions. And we started coming up with this thing that we call the occupancy distribution for some object. And so you can see examples of what that might look like here, where if the object's partially visible here, then we basically just have one area where it could possibly be. And if it's completely invisible, then maybe there's some like heat map over the image of where it might be. Okay, so how do we actually predict this and come up with labels for this? Well, we're going to end up using the same key ideas that we did for the segmentation network. And we're going to, again, use depth images for generalization, and we're going to use simulation for generating labels at scale, right? So again, we can take some target objects like this red thing here, drop a bunch of other objects on top of it to make it look like some of the scenes that we might be seeing in real. Then we'll render some images. And I think this one's a little trickier to think about how to generate labels, right? For segmentation, it's easy. You can kind of just imagine like each object, just look at where that object is in the image and you kind of map that back to the image. For this one, it's a little harder to understand what the occupancy distribution actually means and how we generate it. So just as kind of intuition here, what we're doing is we're basically scaling, we're translating and rotating the object across different areas in the image. And we're going to see, is it still hidden if it were to be at this point, like theoretically. So in this case, like, yeah, it would still be hidden. If we rotate it, move it over here, yeah, it's still hidden. If we move it here, it's not hidden anymore. So that's like not part of the distribution we're trying to do. So if we do this kind of all over the image and move the object all around in different places, a bunch of rotations, bunch of translations, then we can see we're going to end up generating something that looks like this. And so that's how we do it in simulation. We can generate these labels. One other key note here is that if we do this for different types of target objects, even for the same scene, the distribution is going to look quite different. So you can see, again, like bashing your intuition, if this thing has holes in it, you're not going to have any part of your distribution over there. But also as the object becomes longer and skinnier, then there start to be fewer places near the edges of objects, especially that you can actually find the object you're looking for. And And that kind of makes sense intuitively, right? Like when this thing is basically square, you can kind of rotate it all around near the edges of things. But when it's long and skinny, there's only like one orientation probably that actually would make it fit there. So that's also kind of a cool effect. So what we did is we used all these labels and images that we generated to train a network that would predict these types of occupancy distributions, pretty standard training. And then you can see that it works pretty well. So at least on simulated images, and I'll show some real images later on, but it actually is relatively simple to learn this type of occupancy distribution prediction given enough data. And with simulation, we're able to scale that data collection high enough that we can start predicting for objects that we've never seen before. Okay, so yeah, that's a good, hopefully a good understanding of the perception side of things. And I think now we're gonna dive a little bit into the policy side of things. So given these types of intermediate representations, now how do we choose which actions we actually want to take and which objects we want to move at any given time? So yeah, this is now addressing kind of the second question here. And so what we started with, and yeah, it's great to have Andre here also. He was a big part of this. But we started with a bunch of baseline policies where we basically just had a bunch of heuristics. So I listed a couple of them over here, but in this paper, we just tried some different things out that we thought were intuitive. So maybe you would just always pick like the largest object or something like that and see how that works. It actually works like pretty well. So you can see here, I will try to not overwhelm you with results, but basically works pretty well if you just pick the largest object. You want this thing to be kind of up and to the left as much as possible, because that implies that you're extracting the target as quickly as possible. And so if you do some of these types of policies, even in 15 total objects over a lot of different rollouts in sim and real, those policies do quite well. But we also tried it with a human, which in this case was Matt underneath a blanket. So he couldn't see what was going on. And he was trying basically to operate off the same observations that the robot was getting and choosing actions. So we're basically replacing like this high level policy with Matt under a blanket and telling him to choose which objects to move around. You can see like there's still like a decent gap in performance here between whatever the best policy we came up with and Matt. So yeah, and I think a lot of this kind of boils down to this sparse reward problem that we were talking about before. So it's really hard if you just kind of see some scene at the beginning to decide which object to choose, because there might be like a bunch of different object interactions along the way. And maybe even the order in which you pick things is not super important, or maybe it is, depending on how things are lying on top of each other. So one of the key ideas, which was the second part of this occupancy distribution paper, which we called X-ray, was coming up with this surrogate objective, which kind of induces a new type of policy for mechanical search. So again, there's a lot of math here, but the basic idea was that at each time step, we can kind of densify our reward by looking at the support of this occupancy distribution. And so at each time, what we're just trying to do is shrink this distribution as much as possible by taking whatever action basically does that. So yeah, that's all this is saying. It's a serious acronym here, but it's great. Yeah, so this slide also, when it comes up, we'll say the same thing more or less. So we can kind of combine the segmentation, which is at the bottom here, from the first part, with the occupancy distribution, and this is what makes our X-ray policy. So we just essentially overlap the two of these, and we sum up for each object how much distribution is contained within that object, and whichever one has the most amount of the distribution in it, we just want to grasp that object and get it out of the way. So yeah, I think hopefully this makes some sense, but also it really simplifies the high-level policy, right? So what we've done is we've shifted a lot of the burden onto our perception pipeline and said, like, give me a really expressive intermediate representation, and maybe that thing's a little bit easier to learn. And now our policy is actually really simple. We're basically just overlapping these two things and taking whichever thing is the max of those. Okay, so then, yeah, what does this actually look like? So here's a simulation rollout. yeah, basically you can see on the left, we're like keep removing things from the scene until we end up with just the target object visible there. You can see what the distribution looks like as we keep removing parts of it at each time step. So, yeah. Yeah, again, here's some more results. So this basically just was saying, if we try this on a bunch of simulated scenes and also with real scenes, we actually get much better success rates. So yeah, about 15% better success rate than we did with some of the previous policies that we were looking at. Okay, so here's some fun videos too. So here's the case that I was showing you before, where you had the object completely occluded. And so you can see what this policy does. It looks pretty reasonable. It's going to grab something that is maybe most likely, which is the mustard, and then we'll try the next most likely thing. And then again, if it's partially occluded, you can see that it's going to collapse to just that one spot, and it'll definitely grab the right thing that is hiding what we're looking for. Okay. Yeah, and then here's another. These videos are just really fun, so I try to put them in there. You can see again how this distribution is going to change over time. And the bottom here is also saying basically which object it wants to pick up. So which object has the most overlap with this distribution. Yeah, so you can see that we're basically just going to dive right through the pile, trying to focus on objects that we think are basically lying on top of something else. Okay, then I think the last part of this is going to be about how we can use this for shelf type environments. And I'm not going to go too deep into this because I want to let Raven also take some of this for her PhD dissertation talk at some point. But yeah, this is something we've really been thinking about a lot in the last couple of years. And there's a couple big challenges when we start moving towards lateral access environments. And I think I'll try and go through a couple of them, but one main one for me is that objects are really sitting in these very specific poses when they're on shelves. So unlike the bin or the tabletop, like I was showing before, where objects are just all heaped on top of each other, all of the objects in shelves typically are either stacked on top of each other, or they're all just sitting next to each other in really nice stable poses. And then also, I think this is another key thing to think about is we didn't have a lot of control when we were pushing objects in the bin, because we can push one object, but it's probably going to move a whole bunch of other objects around it. In the shelf, it's actually much easier to kind of push or grasp one object at a time without disturbing everything else that's there. Yeah, and so there's two kind of key adaptations or extensions that we made for the lateral access environment, I think. And one was doing this history encoding over the occupancy distribution. And we also collapse it down to 1D. So we can collapse it to 1D because since everything's sitting on the bottom part of the shelf, we don't have to worry about, kind of extending this to 2D over the whole image. Everything is sitting down, right? So if we move something to another place in the shelf, then we can just track it only through this one dimension. And then I think the history encoding is also something that is really key here, because if we're not going to remove objects from the shelf, we need to kind of keep track in some way of which objects we've already looked behind and which ones we haven't. And then the second part of this is this Occlusion tool, which is really helpful for performing these pick and place actions and pushing actions within the shelf. And I'll talk a little bit more about that. So yeah, how does the history actually work? So here you can get a good sense of it. So say we want to move this object here, we might start off with some distribution like this and end up with some distribution that looks like that, right? Because now we've looked behind that object and seen there's nothing there. So we just overlay these two distributions from the two different time steps, and then we'll end up with some minimum. So this is actually a pretty easy way of kind of tracking which objects we've looked behind already and keeping track of our distribution that way. And then in terms of the Occlusion tool, yeah, this is what it looks like in real life. We have this pushing blade and a suction cup, and this is really helpful to both stably push things. So we have that big surface area from the blade, and then also be able to pick and place things without getting our wrist stuck in the way. So those are kind of the two main benefits here. And when we use these suction pick and place actions and suction in the Occlusion pushing tool actions, we're able to get a much better success rate than if we just try and use the robot with its wrist over here, or just use pushing actions. Yeah, so again, I'm not going to go deeply into this, but I'll just show some videos of that as well. It works pretty well in the shelf. I think there's still some more research to be done, but it's definitely really cool that we're able to do this both in the bin environment and also working on shelves where we can be more useful, maybe in home settings especially. Okay, yeah, so that's mostly it. I'm going to talk a little bit about some of the themes that I went over. Hopefully these are clear already, because I think I tried to mention them throughout the talk, but I think some really important things that I've learned about and tried to keep going throughout my research are having these really expressive intermediate representations and action primitives, trying to break down these policies from kind of these monolithic, just take an observation in, push out an action. Instead, we're going to try and shift some of that burden onto perception. Training using simulated depth images, or just using simulation a lot in general for labels to try and move away from having these really expensive hand labels. And then I think the embrace uncertainty, that works for the occupancy distribution, but it also is really relevant for doing experiments with robots in general. Things tend to go wrong a lot of the time. So yeah, this is also for Professor Goldberg. Always tells us to put a failure mode slide. So here's a bunch of failures that the robots can do at different times. Kinematic failures, weird things happening with power on the robot, colliding into things. It happens with pretty much every project. So I think it's important also to kind of embrace the uncertainty of some of that. And obviously try and fix them in the next paper. Yeah, and then here's some also interesting mechanical search challenges that I think are still out there to look at. And some of these we've started looking at already, but I think, like I talked about at the beginning of the talk, humans really go after this problem in a completely different way than maybe we've been looking at with robots, right? So you just kind of dive in there and move stuff around until you find what you're looking for. You don't really do this like single action at a time, pick something out of there, move it somewhere else. And so maybe we can start looking at those types of actions. I also really like this video up here where you're using contacts to kind of push other objects out of the way. That's pretty cool. Yeah, having some closed loop stuff for pushing, grasping, placement, all that. And then I think also this semantic connection, Andre has also looked at this to some degree, but typically when we have shelves, especially, things are not arranged just randomly on a shelf. So can we incorporate some of those aspects of, I like to put my milk bottles next to my eggs or something like that, and understand a little bit better how those things are related so we can guide our search. Yeah, and then stacking also, I just like this figure, so I put it in here. Yeah, okay. So this is pretty much the end. Yeah, I'm gonna go through some thank yous and acknowledgements and all that. Yeah, first of all, definitely thanks to Professor Goldberg. He's been really, really incredible in terms of like guiding my research process, I think. Trying to help me think critically about a lot of these problems. As you can see from the failure mode slide, making sure that we always include the negative side of some of our experiments as well. Yeah, and always like trying to think about what's next. I think that's one of the things that I've always definitely geared up for whenever we submit a paper or something like that, where he's always telling us to plan ahead for the next deadline, or think about how we can improve what we've just finished. So trying to not stay complacent on that front, for sure. Then I think I have a whole bunch of people here. These are all the PhD and postdoc students that I've worked with in the lab. Really incredible time with that. Obviously, we have all the undergrads that I've mentored, or master's students as well, or worked with on different papers. Yeah, I mean, I feel like we have some of the best undergrads at Berkeley, so that's great. It's awesome to be able to work with everyone. These are a bunch of my collaborators, both at Berkeley and at other academic institutions that I've worked on different papers with. And then also all of my industry collaborators as well. So we've done an internship at NVIDIA and worked really closely with people at Google and Siemens on some of these papers. And it's always really awesome to have their insight on all these problems and how they might pertain to some industry problems as well. Yeah, and then I just have like a bunch of random pictures. So this is some lab pictures from various deadlines or conferences presenting all of our stuff. Yeah, these are some of the Ambi folks who I'm excited to join after this. Yeah, this was like from Mars a while back, and I'm really excited to keep that going. These are a bunch of random pictures of friends at different points in time throughout the PhD. I think people always were really supportive of me, and it was awesome to be able to get outside and go on all of these different hikes, adventures, and skiing and hiking and yeah, all that stuff. Running, of course. You know, we also had the Rollout crew during the pandemic, which was awesome. Yeah, obviously, thanks to my family. They've been there the whole time, and also thanks to Katie, obviously my fiance, who's here today, who graciously gave up her desk during the pandemic so that I could work in our house. Yeah, I think that's pretty much it. Thanks to everybody for listening, and I hope you enjoyed the talk. Yeah, I'm really excited to keep working with many of you in the years to come.
Excellent, excellent. Thank you, Mike. Beautifully done and tremendous presentation, I have to say. You presented some work in ways that I haven't seen you before, which are super crystal clear. So thank you for that. I want to just our formality here. We should first turn to Ron Fearing to ask if you have any questions. And then, by the way, we're going to open this up to everyone because technically everyone any member of the public or your family, Mike, can ask you a question, or any of your friends from MIT or Stanford or anything like that. So, but let me turn over. Ron, if you have something to ask, please proceed.
Really nice job. Really enjoyed the presentation. Yeah, I don't have any questions, but congratulations on job well done.
Thank you.
Okay, you're going easy on him, huh, Ron?
Yeah.
All right. Well, thank you. I guess Ron, because he's now emeritus, so he's a little more easygoing than he. Okay. Who else would like to ask a question? Anyone's got a tough?
Yeah, I've got one. So early on, you talked about sort of the human intuition of like if something is more shallow versus deep could play a role. It wasn't clear if that was taken into account, and I'm just curious about your perspective.
Yeah, it's a really good question. So I think for the original X-ray work that's up here, where things are on a tabletop, it's really not taken into account at all. So yeah, it probably wasn't super clear from the way I was describing it, but essentially we're just shifting the object underneath this pile and kind of assuming that things are flat. Now the network does learn some sense of relative depth for objects, but I would say it doesn't do a great job of understanding like how deep objects are in general. And that makes sense because there's a lot of unseen objects that it gets at runtime that like how would it know what the actual shapes are? But I do think for the shelf version of this, there's a much better understanding of that because now you have multiple levels of occlusion typically. So you have objects that are stacked behind other objects. And this is kind of a side effect of training on these simulated scenes, but you do get a sense of if you can see maybe another object behind one object in the scene, there's less of a chance that you're going to find what you're looking for behind there because part of that space is taken up. So the network does actually tend to learn that type of stuff from training data. Obviously, again, like if you put a bunch of objects that are completely outside of training distribution, it's probably going to struggle with that. But in general, it does have some understanding of that. Yeah, it's a really good question.
Yeah. Okay.
Am I going?
Yeah, go ahead.
What is the most memorable or hilarious robot failure mode that you have seen in the last 5 years?
Yeah, actually, it's a good question. We were watching a bunch of videos yesterday from the mechanical search paper, the first one. And I think, yeah, there's just like innumerable failure modes there. It's the most frustrating thing to watch the robot be able to see the object that it wants to grasp and then like not be able to plant a grasp on it or like try and plant a grasp there and just like stop because it's reached some kinematic limitation or something like that. Like I think those are like always the most frustrating things because you're so close, you know, your system is outputted like exactly the right thing you want to do, and then you just like can't plan there. So those were always the most frustrating. We have a lot of videos of those. I didn't put a bunch of those videos in here because they're not very exciting to watch, and I feel like if you watch them, you're gonna watch like 4 steps of it trying to do something, and then it just fails at the end. You're like, all right, I guess that's the end. But yeah, it's definitely the most frustrating.
Good. Okay. Other questions? Okay, I'll have to ask one. So, Mike, I really appreciate that you talk about the failure modes, and I'm glad that you actually see it as a good thing now, because I do think this idea of embracing the failure is so important, because that's where we learn things, right? I mean, just reporting where the system works, that's what a lot of papers do, but that sort of confirms maybe the expected. But what's really, I think, takes papers to a new level is when you really pay attention to where it fails, because that's where there's more something interesting going on. And you've certainly, you know, you've been very actively involved with physical experiments in the lab. You've been sitting next to the robot for years now, and lots of experiments. Your incredible patience you've developed to work through all the nuances. And by the way, I also want to say, for everyone's benefit, Mike only talked about really part of the work that he's done here at Berkeley. He's actually done many other things that he didn't have time to include, but he's in fact, and his role in mentoring these students. And you looked at adversarial objects, and you've looked at pushing and detailed model of grasp mechanics. So there's a lot more here as well that you've contributed, and it's really an incredibly strong body of work. Here's a question that I get often, and I'm curious what your answer would be, which is people say, well, what if you had an extra sensor? In particular, what if you had tactile sensing? What do you think that would, how do you think that would change grasping for robots?
Yeah, that's a good question. I think tactile is definitely a hot button topic. I think it can be really useful in a lot of scenarios. So, you know, especially in cases where you can't necessarily see what contact you're making, something like that. With vision, like in almost all of these papers, we've only considered a case where you have a single view of what you're trying to do. So I think, yeah, in a lot of those cases, tactile can be really helpful. I think the main downside is it's typically really brittle, and it also is really high dimensional signal, typically a lot of noise. So it's hard to maybe sometimes map the signals you're getting from tactile sensors to what you're actually trying to do, like whatever task it is. So I think, I mean, it's definitely an active area of research. I know your group is also doing a lot of research with that. So I think it definitely has a place in the future. Like some tasks definitely require tactile sensing, I think, but there's definitely still a lot of work to be done in terms of how to incorporate that most effectively in some of these tasks. Yeah.
Great. Okay. Good answer. And then last, what about your next steps? What are your plans, and where do you see your PhD in sort of helping in the next stage of your career?
Yeah. So I mentioned briefly that I'm going to be working at AMD with a bunch of the people that I started off doing my PhD with here. And I do think like a lot of this is hopefully relevant there. I think, but I think like in general, you know, wherever I end up in many years, I think it will be helpful just to have thought about problems the way that we think about them in academia and research. So I think, you know, yeah, just like trying to do this like thorough evaluation of different methods and trying to understand how to design experiments to test some of the things that we're trying to do. Like that's probably the most valuable part of doing research. So I think, you know, you can always learn new things and go to different fields and all that stuff. I certainly did at the beginning of my PhD already. So
excellent. Okay, great. So unless
we have another question.
Okay.
Yeah. So your talk was really smooth with all these like amazing plots that I'm gonna have to ask you how you made them later so I can make it myself. But were there ever, I mean, it made me wonder if there are any points where you felt really bottlenecked, and if you did feel a bottleneck somewhere, you felt blocked at some point during your PhD, what got you unstuck?
Yeah, it's a good question. I think For me, with the way that my projects ended up working out, I think I always had like multiple projects that I was working on. And I think that helps a lot with that, because I think, I mean, this is a function of our lab as well, but you're always mentoring several undergrad students, several master's students, and you're typically involved in a couple different projects. So I think the main thing for me is just trying to shift some focus sometimes and let some of these projects sit a little bit. You know, for the X-ray stuff, I think like we did some work on that, and then I went away for an internship for the summer, and then like came back and worked on it some more. So I think that also like helped out with that.
Yeah. Like forcing some time off.
Yeah, exactly. Like just working on a different project for a bit.
Good. Okay, great.
Just one question.
Okay.
As a now expert in grasping, do you see the field going more towards, you know, being end to end, maybe goal condition stuff, or do you see it maybe staying in its current route of success, like more semantic information from the vision side being incorporated into, you know, more more model based manipulation approaches?
Yeah, it's a loaded question, I think. Yeah, I don't know if I would say that I'm an expert, but I think I think there's room for both. Like, I think it really depends on the problem you're trying to solve. Like, if you have a really good understanding of what objects you're trying to grasp, I think it's usually easier to not do something that's end to end and maybe hard to interpret, right? I think it's much easier in that case to use a lot of these more model-based approaches that are easy to understand and usually work really well. But yeah, I mean, if you're trying to, you know, AGI is like the big thing these days, right? Like, who knows what's going to be necessary for that? But I do think that it's going to be harder to rely on like all of these model-based approaches or like all that to solve like every possible grasping problem, right? But maybe you don't ever really need to do that. So I think that's kind of like the trade-off there. I mean, you're always like, if you're specializing for some set of objects, then it's usually better to go all in on specialization for that.
You know, I love that. I heard somebody whispering, "What's AGI?" And then so that's artificial general intelligence, and I think for anyone who's worked with real robots like you, Mike, we probably agree that that's far off.
Yeah.
Humans have many good years left, so don't worry.
Yeah.
Okay, all right. Well, listen, I thank you so much, Mike, and also your family for being here, for doing such a good job raising him. He's fantastic. I want to thank all of your friends who are here, your colleagues, you've got a huge group of people who are behind you and support you. And Katie, I want to wish you all the best. You made a great choice. He's a fine gentleman, and he's a great scholar, and now we can call him doctor. So congratulations, Mike. All right. So thank you all for this. We have to do a little bit of paperwork, and Ron and I will have to sign off. But I don't foresee any major obstacles. I think it's safe to assume that you've passed the bar, Mike, and I want to say congratulations. It's a very, very wonderful step. So very proud of you, and it's a real honor, and I'm looking forward to celebrating with you next week. Okay. Bye, everyone.
Thank you.
We brought so much cake.
Sorry about it.